Good morning. Uh, Big crowd today. Fun. Monday morning. You want to start your week off right. So, just as a heads up, I'm going to have you guys for this week, but Wednesday there are no classes, right? Because of Remembrance Day. So I actually only get you guys Monday and Friday this week. So, anyways. But I will be teaching you this week. Okay. No classes on Wednesday for Remembrance Day. All right, so I guess I'll just see you today and Friday, and then we'll kind of check back. If you don't hear from, I don't think anyone sent out a message to you guys, but I'm glad you're here. You kind of figured out that this is where you need to be, so that's good. Shaun will let you know when he's back. So until then, we'll just keep meeting here, and that's good. All right. So last day, I kind of introduced all this stuff, a bunch of stuff. So let's see here. We talked about, so I'm just going through the notes from 2.6. So we finished 2.3. We talked about increasing, decreasing, etc. But that's from last day. And then 2.4, 2.5, we kind of skipped through. Just a quick note on the average rate of change. And then we talked about transformations of functions. And so what we do is if we want to transform a graph and look at a graph of x squared plus 3, what you have to do is you have to identify the core function, okay, and then manipulate that function. And so how we manipulate it is kind of outlined in these blue boxes. I'm cheating, I'm stealing these blue boxes, but I think it's just nice to have them nice and compact with a little image. So if we have f of x and we're adding or subtracting c, well then we're adding or subtracting from the y values, right? So those are going to be vertical shifts. Okay. Whenever things are manipulating horizontally or manipulating x, I find that it behaves the opposite of how I expect it to. For example, when you have x minus c, notice how this minus c is now on the x. So x minus c actually shifts it to the right by c units, whereas in my mind, I would want it to shift left, but it kind of does the opposite of what you want. So that's just something that we have to remember, right? And so if you have x plus c, then you have to remember to shift it left c units. Okay. And we looked at combining horizontal and vertical shifts. And what we said is that, okay, if we have a core function, right? In this example, it was root x. We can pick 3 points is usually enough, and follow those points through the transformations, and then we'll be able to graph this new graph. So that's what we're going to do today. Just as a review example, we didn't really get to do many examples. We did a few, but not many. So I want to start with kind of a big one. We can reflect graphs. Okay, so if you're taking the negative of f of x, that's essentially negative y, right? Remember, y is f of x. And so negative f of x just means that all your positive y's are going to be negative and all your negative y's are going to be positive. So that's going to be a reflection around the x-axis, right? Whereas here, if you have negative x, right, on the inside of the function, then you're reflecting around the y-axis. Okay? All your positive x's become negative, okay? But your y's stay the same. If you have c times f of x, Notice that it's important that we know, oh, hey, what happened here? Your screen sharing, okay. It's telling me my screen sharing ended unexpectedly. Okay. Let's
Good to know
try.
it can tell the truth.
Say that again.
Good to know it can tell the truth.
Yeah. Exactly. Hopefully, okay. Looks like we're back in business. All right. Hopefully it'll hang in there. I don't know why it didn't. Hey. Why I lost it. Anyways. Who knows? And so if you've got the C, so notice the f of x, that's what I was saying. So why is f of x? So if the C is manipulating the f of x, then you're manipulating things vertically, so on the y. So if C is greater than 1, then you're going to stretch by a factor of C. So then you stretch it like this, and if it's between 0 and 1, then it essentially shrinks vertically by a factor of C, right? Where C is going to be between 0 and 1. However, if the C is on the x, right, so not on the f of x anymore, just on the x, then we're working horizontally again. And so what we have to keep in mind, and this one's probably the hardest one to remember, and so I would encourage you to kind of make a note of it and have it handy. In fact, all these blue boxes would be nice to have handy, right? And so, and just kind of memorize them if you have to. I don't know what Shaun's testing methods are. I don't know if it's kind of open book or if you're allowed to have some notes or not, or but depending on what his method is, these are going to be good to know, right? All these blue boxes in the 2.6 notes. So if C is greater than 1, right, then you shrink the graph horizontally. So you shrink it horizontally by a factor of 1 over C. Okay, so that's kind of weird, right? But it's just something that we have to remember. And then if C is between 0 and 1, making it a fraction, right, then you stretch it horizontally by a factor of 1 over C. But what we said was, okay, if C is something like 1/2, right, then we stretch the graph horizontally by 1 over C, which is 1 over 1/2, which is fraction over fraction. So we flip and multiply and we find that it's 2, right? So we stretch it by 2. So it behaves a little bit wonky. Okay. Then I just plowed through and we talked about even and odd functions. We're going to do a couple of examples. But a function is even if you're able to take the negative x and manipulate it so that you just end up with the original function f of x. It's odd if you're taking the negative x, so you plug in negative x for all your x's, and you're able to manipulate it so you get negative f of x. And I'll show you a couple of examples. There are functions that are neither, right? Neither even nor odd. You can look graphically, right? If a function is even, it's going to be symmetric with respect to the y-axis. If a function is odd, it's symmetric kind of across the, with respect to the origin here, so kind of on the diagonal, which is kind of weird, but, right? And so for figuring out if functions are even or odd, what you do, notice you take the negative x, negative x. So you start the same way. And then what you're able to do is you just manipulate it until you're able to either land on f of x or negative f of x or neither. Okay. So let's do, where were we here? 9th. Just for some review. We looked at transforming graphs. Transforming graphs. Okay. And so, for example, if we actually, make it even harder. since I'll walk you through it and kind of hold your hand, so we can do some hard stuff. So find the graph of 4 minus 1/2 times x minus 1 squared. Okay. There. All right. So the first thing that we need to do is we need to identify the core function. And the core function, I think it was in our 2.2 notes, it was that big table of graphs, things like x to the power of 2, x to the power of 3, x to the power of 4, what do they all look like? So any x to an even power is some sort of parabola, right? X to an odd power is this kind of dancing guy. You can have an even root, so a square root just kind of goes like this, and then an odd root goes like this, if I can do it like this. So we need to know those shapes, right? Absolute value is this kind of V, and what else do we have? I think those are the core ones for now, right? And so here, what I'm seeing, if I boil it all down, it looks like x squared has been manipulated, right? And so what I'm going to say here is it looks like our core function f of x is x to the power of 2 has been manipulated. Okay. So what we're going to do is we're going to remember what all these kind of manipulations look like. And just to make it easier, I want to follow, let's say 3 points. I want to pick 3 points on x squared, and I want to follow them around through my transformations. But first, what I'm going to do is I'm going to just outline what these transformations are, right? And so here, let f of x be x squared. Okay. Working from the inside out, right? The first thing that's happened is I've taken x minus 1, right? X minus 1 squared is just one manipulation on x squared. So now, let's say here, the first step is x minus 1 squared, okay, is x squared shifted 1 unit to the right, is x squared shifted 1 unit to the right. Notice x minus 1, you might want to bump it to the left, but that's no. Whenever we're manipulating x here, right, we have to move to the right. It's kind of the opposite of what we want to do. So x minus 1 shifts us to the right 1 unit. Shifted 1 unit to the right. To the right. I always want to combine words, the right. Okay. So now, right, we could pause and we could graph x minus 1 squared, right? But what I'm going to keep doing is, so I'm going to just keep manipulating this thing until I've built this entire thing. Okay. So if I do, I'm just going to ignore this negative for a bit. This negative is going to reflect around the x or the y axis. We'll see, right? But now I've got 1/2 in front of my function, right? So this is essentially c times f of x. So I'm gonna, well, we can say stretch, but stretch it by a factor of 1/2. And so that's essentially shrinking. I'll use a different color so that I can kind of match these later on. Okay, I'm going to leave a space here because what we're going to do is we're going to follow 3 points around. So I might put them here. We'll see how we do for space, but just leave a space there. So the next thing we have to do is 1/2 times x minus 1 squared is x minus 1 squared shrunk vertically by 1/2. Or I'll say just in general, stretched vertically, doesn't matter, by 1/2. Okay. Again, I'm going to leave a space there to kind of follow some points around, right? So notice here, so now I've kind of built out from here. My next step is to take the negative of this thing. So negative of a function is a reflection around the y-axis, or sorry, the x-axis, because my y's are becoming negative, right? So if I have a positive y, it becomes negative with this negative in front of the function. So negative 1/2 times x minus 1/2 is 1/2 x minus 1/2 squared, or x minus 1 squared, reflected about the x-axis. Okay. All right. Now, what color haven't I used? Purple. Very similar though. Last thing I need to do here, right? So it looks like I've kind of worked my way out. So you just kind of snowball your way out. And here I'm adding 4 to the overall function, which means I'm going to shift up by 4 units. So 4 minus 1/2 times x minus 1/2 squared is negative 1/2 x minus 1 squared. I keep saying 1/2 again, but it's just x minus 1 squared. Shifted up 4 units. Shifted up 4 units. Okay. So what we can do to graph this thing is we can pick 3 values on f of x equals x squared. Okay. So to graph this, function, pick 3 values, or more if you want, but we'll only need 3 values. On f of x equals x squared to follow through these transformations. Okay. So I guess what I'll do, I'll try to squeeze them in on this, on a table here. But first of all, I want to just have a quick graph of x squared, right? So f of x equals x squared, we know looks like just a parabola like this. And so that's where I'm starting. And then I'm going to be manipulating this thing, shift it over, stretch it vertically or shrink it vertically, and then reflect it and then bump it up, right? And so here we go. So f of x, equals x squared. I'm going to pick 3 points. Okay. Let's do, so I know what x squared behaves like, right? Any negative value becomes a positive value. So what I'm going to do is I'm going to pick x equals 1, -1, and 0. Right? So I'll start here, -1, 0, and 1, and I'll follow those through. So I have, if x is -1, -1 squared makes 1. Okay. 0, 0 squared is 0, right? Which makes sense because you start at the origin and then it just kind of, this a default parabola blooms up. And then if x is positive 1, then x squared is also 1. 1 squared is 1. Okay. So now what I'm going to do is I'm going to follow these. So x squared is shifted 1 unit to the right. So that means all my x's, I'm going to add 1. So here, x minus 1 squared, I'm going to add 1 to each of these x's, right? Shifting everything to the right. So this becomes 0, 1. My y's stay the same. 1, 0, and 2, 1. Okay. So we've handled x minus 1 squared. So now I want to do 1/2 x minus 1 squared. Notice that my points are already at x minus 1 squared. So what I have to do is I have to stretch it vertically. So multiply all my y's by 1/2. Okay. And what color was I using? Pink. So 1/2 x minus 1 squared. Okay, so each of my y's, I'm going to multiply by 1/2. So that becomes 0, 1/2. 1, 0 times 1/2 is just 0. And 2, 1/2. Okay. All right. So now I've stretched my points or shrunk them vertically. Next thing I have to do is I have to reflect about the x-axis. What does this mean? It means all my y's become negative. So here, what I'm going to do is all y values become negative y, right? So if it's a negative, if the y value is negative, then negative y makes it positive, right? So I just want to highlight that. In this case, we have just shifted over to the right by 1, and then we've shrunk it, so all our y values are positive, so now they're going to be negative. Okay. And so here, negative 1/2 x minus 1 squared, all I'm doing is each of my y values is going to be negative now. Okay. And so I get 0, negative 1/2, 1, 0, 0, negative 0 is just 0, and 2, negative 1/2. Right. X values stay the same, but the y values flip. And finally, we're getting there, right? The last thing I have to do is shift up by 4 units. So to each of these y's, I need to add 4 units. So 4 minus 1/2 times x minus 1 squared becomes, so negative 1/2 plus 4 puts me at, I'll say 3.5, just because I want to plot these points so it's easier to have them as a decimal. You want to be careful, right? Because if you're not landing on an exact number, then you're rounding and it just depends. But usually if we're graphing, we can use decimal approximations. 1, so x is still 1, but the 0 gets bumped up to 0 plus 4, which is 4. And 2, negative 1/2 is also going to get bumped up to 3.5. Okay. So now I can plot these points and I can just kind of, well, I'll just sketch them quickly here. X-axis, y-axis. So let's say this is at 2 and 4, just because I didn't do a very good job of sketching these. 1, 2, 3, 4. Sure, 1. How about that? How about that? So let's see here. I'll use just blue. So 0 is and 3.5. Okay. 1 and 4. 2 and 3.5. Okay. Knowing that in general, this thing is going to look like a parabola, right? It looks like I've got a maximum here at 1, 4, and it's just going to go down like this. Oops. There. Okay. Let's check it in Desmos just to make sure that we did the right thing. I think I was even, I think I even had it here, but let's start over. 4 minus x, oops, sorry, I missed the 1/2. 1 divided by 2, make sure you step out of that fraction, otherwise you keep doing it on the 2 in the denominator, which is not what you want to do. X minus 1 squared. Okay, looks like 1, 4, 0, 3.5. And if we moved over here to 2, is that 3.5? Another thing I could do is I could draw a line at y equals 3.5 and then figure out where these intersect, because those are the points that I have on my graph, right? So I just want to make sure that they ended up in the right place, which they did, right? And so here, looks like we did it right. So you just got to break down the function and follow a couple of points around, and then you can plot them knowing the general shape. So that's going to be the important part, like I said, to know those core functions. What are they going to look like in general? Okay. Nice. Use Desmos to check your work. Okay. You always want to make sure that what you did makes sense. All right. So I did give you last day, let's see here. I gave you a bunch of different transformations you can try. So first step, right? Figure out what the core function is. What function are you following around? Pick a couple of points on that function, right? And all you're doing is plugging in different x values and figuring out what the y is. And then you have some points that you can follow around. And then, of course, check your work using Desmos. So all of these you can graph in Desmos just to make sure that what you did was correct, right? So just try these. Okay. You don't have to do all of them. I'm not assigning them or anything. It's just if you want to make sure that you're really good at doing transformations, then here they are. Practice. All right, so let's do some examples of even and odd functions as well. So like I said here, for even functions, you take the negative x, so you have some function and you take the negative x value and you can manipulate it. And if you can end back up at negative or at f of x, then it's even. Same thing, so you start the same way, but if you end up at negative f of x, you have an odd function. Okay. So I'll call that the end of your review, but also recall that if f of negative x is equal to f of x, we say f of x is an even function, I'll say. And if f of negative x is negative f of x, we say f of x is an odd function. in general, right, even functions are exactly what you kind of probably suspect. So x squared is an even function, x to the power of 4. So if we have these um, even powers, then you usually have an even function. There are some cases where you've shifted off or done something to it that doesn't make it even, but in general, an odd function, same idea. If you have an odd power, right? Because if you take negative x into x to the power of 3, for example, so negative x to the power of 3, then you get negative x to the power of 3. So, which we'll see, but then you have an odd function. So generally speaking, you can look at the power and figure out if it's an even or odd function depending on the power. So we can look at this graphically. Okay. We can decide if a function is even or odd from its graph, right? Even functions have symmetry about the y-axis. Okay. Whereas odd functions have symmetry about the origin, which is kind of on the slant. Have symmetry about the origin. A little bit harder to see. Okay. So you can look at graphs, but what I want to do is algebraically, so using this type of proof, we'll say, to figure out if things are even or odd. All right, and so just as an example for the graphically, f of x equals x squared is even, right? Because you have this kind of, you have this kind of symmetry about the y-axis. Okay. Whereas f of x equals x to the 3 is odd. And remember what it looks, hey, what happened there? Okay. So it's going to be odd. Remember what it looks like is you have this kind of, and so here's the origin and where you have the symmetry, so you can kind of swing it around. It's really weird to think about. Here, I'll show you on this one here, right? And so it kind of swings this thing around on the origin, right? And so it looks weird, right? And that's why I prefer to use just the algebraic way of proving if things are even or odd. So this kind of swings, swings around. Here, I'll just do this. If that makes sense. It's not very pretty, is it? We will focus on using or on proving even and odd functions algebraically. So we will use algebra to determine if a function is even or odd. Oops. Okay. So step one for whatever, if you want to know if it's even or odd, step one is to, in your f of x, replace all your x's with negative x. So replace all x's with negative x, right? So now you have f of negative x. Okay. Your second step is to manipulate it until you have simplified it so that it either looks like f of x or negative f of x, or neither. Manipulate / simplify the function until you have f of x, which means you have an even function, or negative f of x, which means you have an odd function, or neither of those two, neither even nor odd. Oops. Okay, so it just depends on where you end up at, and it's totally fine to not end up at either of these. Okay, so let's do some examples. Determine if the following functions are even, odd, or neither. Okay, so the first one we're going to do is f of x equals 2x squared minus 4. First thing, I see this x squared, so I suspect it might be, what did I say, odd? Even, if anything, right? And so what I'm going to do is, step one is to replace all my x's with negative x. Okay, so f of negative x is going to be 2 times negative x squared minus 4. A negative squared just becomes x squared, right? Negative x squared just becomes x squared. And so this I can rewrite as 2x squared minus 4, which is my original function, which is f of x. Therefore, f of x is even. Why do I keep saying odd? Ugh. Okay. What if we try another one? What if f of x is 3x to the 7 plus 4x to the 3? Notice that both of these have odd powers, right? So just my gut, I suspect that if anything, it's going to be an odd function, right? So you want to kind of develop this this kind of survey approach where you kind of suspect that it's going to be even or odd, and then you want to confirm it, right? That'll make it easier to manipulate your function later. So again, we start and take f of negative x, right? So replace each of these x's with negative x. So we get 3 times negative x to the 7 plus 4 times negative x to the 3. Remembering how negative behaves inside an odd power, we just get negative x. So this becomes negative 3x to the 7, minus, because the negative gets brought outside, minus 4x to the 3. Now what I'm going to do is I'm going to pull out a common negative to make it look like negative f of x. Negative 3x to the 7 plus 4x to the 3, which is negative f of x, Therefore, f of x is odd. Okay. How about a last one? All right, so far things have been falling out just the way that we kind of expect them to, knowing how these powers behave, if the powers are even or odd. Oopsies. Let's try f of x is the absolute value of x minus 3. So remember, the absolute value of a negative is just the positive version of itself, right? And so what we do is we take f of negative x, which is negative x minus 3. What I can do, I can manipulate this and I can pull out a negative, but the negative stays inside the absolute value, right? And so what happens is if I pull out a common negative, I get negative x plus 3. So that doesn't really get me anywhere compared to the absolute value of x minus 3, right? And so sometimes, sometimes, I wanted my pointer still, sometimes it's going to be easier to look at f or negative f of x, because I know this doesn't look like x minus 3 or the absolute value of x minus 3. So then my other option is to see if it's odd. This does not look like f of x equals the root or the absolute value of x minus 3. Therefore, it's not even, right? If it was odd, then we could say, well, then f of negative x must be negative f of x. So what I need to do is I need to look at negative f of x, negative absolute value of x minus 3. Well, that's not this either, right? Since negative f of x is the negative absolute value of x minus 3, which is not equal to the absolute value of negative x minus 3, f of x is not odd. Therefore, f of x is neither even nor odd. Okay. So sometimes you're going to kind of hit a glitch here and find that, okay, well, it's neither. And just remember, okay, not all functions are even or odd. They can be neither. In fact, it's more common that they're neither. But if we're asking you to find if it's even or odd, then usually it's one of the two. But just wanted to show you what it looks like if it's neither. Okay. So let's talk about, hey, nice break here. I've got a page break and everything. Yeah. The little things. Any questions before we keep going into section 2.7? So we're moving right along through chapter 2. So we're going to do 2.7 and 2.8. And then next week, hopefully we'll finish that this week, and then we'll start chapter 3 next week. Either with me or with Shaun, time will tell. Hopefully he feels better by then, but that's more for him than for me. I don't care. 2.7 is on combining functions. Combining functions. So combining functions, we can take two functions, 2 or 3 or 4. We can take as many functions as we want, and we can create new functions by combining them, right? And so the simplest form, we can add, we can subtract, we can multiply, we can divide functions. So those would be pretty simple combinations. Okay. We've talked about the domain of functions, well, we have just a little bit, but I'm assuming Shaun has talked a lot about the domain of functions. And so the domain of functions are all the possible input values of x. And so what happens when we combine functions is we have to really keep in mind how the domain of these combined functions changes. So we can combine functions algebraically. Algebraically just means plus, minus, multiplication, divide, right? So don't be kind of deterred. So we can combine functions algebraically by how we say it is f plus g of x. So here I'm making a new function f plus g of x. But all we're going to do is we're going to do f of x plus g of x. So nothing really changes. F of x plus g of x. Okay. Same thing, f minus g of x, making a new function, but all I'm going to do is I'm going to take f of x minus g of x. I can do I skipped straight to division. That was my bad. F times g of x is f of x times g of x. And then finally we can divide f divided by g of x is f of x over g of x. Okay. Each of these are going to have a domain, right? So the domain of each of these is going to be just the overlap of the domain of f of x and g of x. Okay. So the only time that changes is here where we say g of x can't be equal to 0. Okay. G of x can't be equal to 0, right? If we're dividing, we have to make sure that we're not dividing by 0 because that's illegal math. Okay. So if the domain of f of x is a, okay, so just some set a, all real numbers, for example, right? If you're allowed to put any number into f of x, then the set of real numbers would be a. Or if x can't be equal to 2, for example, if I'm dividing by x minus 2, then a would be all real numbers except x equals 2. So if the domain of f of x is a, and the domain of g of x is b, the domain of f plus g of x, we know, how do I want to say it? I'll say then. So if the domain of f of x is a and the domain of g of x is b, then the domains of f plus g of x is a and b, which is the overlap of a and b. Okay, I'm going to shift this over so I can have room to write that. The overlap of a and b. Okay. It's going to be the same for all of these with the restriction on the division. So that g of x can't be equal to 0. So f minus g of x is a and b. F g of x is a and b. And f divided by g of x is a and b. And g of x cannot be equal to 0, right? So we have that added condition that g of x can't be equal to 0 on top of the overlap of a and b. So notice when we're doing these combinations, right, it's helpful if you're able to find the domain of f of x and the domain of g of x, and then find a and b, because that's going to be the domain for all of these, right? And with an extension on the f over g of x, which is that g of x can't be equal to 0. So where are we here? For example, if we let f of x be x squared and g of x be the root of 2 minus x, okay, find f plus g of x, f minus g of x, f g of x, and f divided by g of x with their domains. Okay. Okay, so I've got a function x squared and the root of 2 minus x. So there are no restrictions on the x that I can put into x squared, right? I'm allowed to square negatives, I can square positives, and I'm able to get a value for each of these. We need to remember, right? So remember, we can't divide by 0, and we can't take the even root of a negative. Okay. So here we've got a root, a square root, which is an even root, our most common root, right? So the square root, we can't take the square root of a negative number, which means that 2 minus x has to be greater than or equal to 0. I can take the square root of 0, that's allowed. Right, puts me at 0. But 2 minus x, as long as x gives me values which are positive, right? So we've got restrictions on the domain of g of x, but no restrictions on the domain of f of x. So here, the domain of f of x is the set of real numbers, or if you prefer, from negative infinity to infinity, right? And when we're finding the overlap, it might be easier to talk about interval notation, right? So if you're talking on a number line, here I can go from negative infinity to positive infinity. The domain of g of x is that 2 minus x has to be greater than or equal to 0, right? Which means that if I add x to both sides, well, x has to be less than or equal to 2. So what this looks like is 2 is greater than or equal to x if I add x to both sides. Usually we talk about x on the left-hand side, so that's how we like to read it. So all I'm going to do here is I'm going to revolving door this thing. So I'm not changing anything. X, notice that the arrow is pointing towards the x still. Okay. So the overlap, right? If the domain of f of x, we called it a, is from negative infinity to infinity, and the domain of g of x is less than or equal to 2, okay? Then the overlap of these domains Well, if we're allowed any number here, our only restriction is that x has to be less than or equal to 2. And so the overlap of this is just going to be x is less than or equal to 2. Okay. So let's see here. If I want to find f plus g of x, I've already found its domain, so now it's the easy part, right? F plus g of x is going to be, let's see here, f plus g of x, oops, is f of x plus g of x, and sometimes you're able to simplify these things a little bit. F of x was x squared, and g of x the root of 2 minus x. Okay. There's nothing I can do to simplify this, and so the domain of this thing is that x has to be less than or equal to 2. And you can just check it here, right? It looks like as long as x is less than or equal to 2, I'm landing on reasonable values. So the domain here is that x is less than or equal to 2. Right? That's going to be the same for all of these with the restriction when we get to f over g of x, because g of x can't be 0. Right, so then we would need to alter this to be 2 minus x has to be greater than 0. Right, all we're changing is the bounds here, so x has to be less than 2, can't be equal to 2. But we'll deal with that once we get there. Let's do f minus g of x. Oops. F minus g of x is f of x minus g of x, which is going to be x squared minus the root of 2 minus x. And again, the domain is that x has to be less than or equal to 2. Fg of x is f of x times g of x. Okay, so we get x squared times the root of 2 minus x. Still, there's nothing I can really do to simplify this thing, so that's okay. The domain is still x has to be less than or equal to 2. Notice all we're doing is we're creating these bigger functions, right? So we're creating these new functions that we could use, right? And then finally, f divided by g of x is f of x over g of x, which is going to be x squared divided by the root of 2 minus x. Okay. The domain here is that x has to be less than or equal to 2, right? The overlap, and g of x can't be equal to 0, which means that, well, 2 minus x, if x is 2, right, then I get 2 minus 2, the square root of 0 is 0, so that's bad news, right? And so the domain is going to be x has to be less than 2, but can't be equal to 2 anymore because we can't have it equal to 0. Good. Okay. You can combine functions graphically, especially if you're adding. It's easy to see. So if you have two functions, what you can do graphically, if you're adding those two functions, is you can just bump up the y values. But that's not something that we're going to do. It's just something that's good to know. So this is what's important, right, for combining functions algebraically like this, right? So you can find the domain first. That's going to be the easiest thing. Otherwise, you're just always finding the overlap and always finding the same thing. So if you start off and you find the overlapping domains, then you can use it all the way along here. But then adding and subtracting, multiplying, and even dividing functions, you just plug them in, right? So not really a huge deal. I'll just make a note here. So a note, we can add two functions graphically by adding the y values of their graph. Okay, that's just something that's good to know. It's not terribly important. Okay, good. So adding, subtracting, multiplying, dividing functions, that's all good to know. And it's good to be able to recognize that, hey, it looks like I've just added two functions. So, but usually what we're doing is a little bit more complicated, and that's what we call compositions. So function compositions is when I have a function f of x and a function g of x, and I'm going to use g of x inside f of x. So I'm putting a function inside a function. So function composition. We can combine functions by using a function inside a function. By using a function inside another function. So this is what we call function composition. And it's going to come into play a little bit in section 2.8 as well. So we need to be really good at function compositions, and they can be a little bit tricky at first because we have to keep our heads on straight and say, okay, I'm plugging this function into this other function. So what we do is we denote it by f and then a round circle. So it looks like fog, right? But really how we read this is f composed with g. Composed with. So f composed with g, okay, or kind of slangy f of g, because what's going to happen is I'm going to plug in g in place of x. Okay, so usually what we do is, again, we have this is the new name of the function, f composed with g of x. But really all we're saying is that that's the same as f of g of x, right? So usually when I see this fog, right, f composed with g of x, how I read it is f of g of x, right? Because then I remind myself that g of x is going and replacing x in f of x. G of x replaces x in f of x. So a little bit trickier, right? Especially if we're talking about the domains of these things, right? And so f is going to have a domain, g is going to have a domain. What we need to do is we need to make sure, okay, so all my x's, so I have to find the domain of g of x, but then I also have to look at the range of g of x and make sure that the range is going into f of x and it's allowed to go into f of x. So that can be kind of tricky. To find the domain of f composed with g of x, right, we need to find the domain of g of x. Okay, so first of all, I'm plugging g of x in there, so I need to find the domain of g of x because it needs to be able to happen. Then ensure the range of g of x is defined in the domain of f of x, right? Because now my outputs of g of x have to be the inputs, right? If we're looking here, my outputs of g of x have to be the inputs of f of x. So the range of g of x has to go into f of x, and that's the hard part, right? And so, and ensure the range of g of x is defined in the domain of f of x, in the domain of f of x. So usually we can do this for the functions that we're doing. We can just look at the composite functions and figure out the domain from there. Unless we've canceled some stuff, then it makes a mess. But let's do an example to see what we mean here. So for example, if f of x is the root of x, right? Here, remember, the domain of f of x then must be that x is greater than or equal to 0, right? I can't take the square root of a negative number. So the domain here is that x must be greater than or equal to 0. Okay. I'm just adding that in as I go, but g of x is going to be x minus 3. Make a note here. The domain of x minus 3, I can plug in any value of x and there's no illegal math involved. So the domain here is the set of real numbers. I can plug in any value of x into g of x and it's still allowed. So what we're going to do is we're going to find f composed with g of x, g composed with f, so I can do them in a different order, right? But now I'm plugging in f of x into g. I can also do a composition of f composed with f of x and g composed with g of x. So find these and their domains. So it's helpful to find the individual domains, and then we can kind of rely on that later. So we'll start with the first one, f composed with g of x. I usually just rewrite it right away, f of g of x. Okay. What I like to do, and you can kind of replace g of x with x minus 3 and then plug in x minus 3 into the root. I actually like to work the other way, but it doesn't matter. As long as you end up at the same place that I do, then you did it right. Okay, so I'd like to replace the f with the root x and keep g of x. So rewrite f of x as the root of g of x, right? Just replacing any x's in f of x with g of x. And then I can look at g of x and then replace the g of x with x minus 3. So this becomes the root of x minus 3. Okay. The domain here, okay, if we go back to this little blurb here, so we need to find the domain of g of x if we're looking at f composed with g of x. So g of x has a domain of all real numbers, right? Which means my output values, I can find any output values, so the range is also all real numbers, right? But now I need to put a restriction on that and say, okay, well, f of x, I can only have inputs larger than or equal to 0. But all I can do here is I can just look at this and say, okay, well, my domain here must be x is greater than or equal to 3. Okay, so the domain here greater than or equal to 3. Let's look at g composed with f of x. Well, that's g on the outside and then f of x on the inside. So again, what I like to do is I like to start with g of x, which is x minus 3, but just replace all my x's with f of x. So I get f of x minus 3. Well, f of x minus 3 is just root x minus 3. So here, my domain is going to be, I'm allowed to put in any f of x into x minus 3, right, or f of x minus 3. So there's no restrictions there, but there are restrictions on f of x. So x is greater than or equal to 0. And most of the time, we can just look at the composite function, right, once we've found it, to see what the domain is. What if we have, the next thing we wanted to do was f composed with f of x. Got a page break, so I'm gonna put it at the top of the page. f of x. So what I'm gonna do here, f of x is root x, so now I'm taking the root of f of x, right, I'm allowed to do that. So this is the root of f of x, which is the root of x. If I manipulate it with exponents, right, I've got x to the 1/2 and then to the 1/2, which is x to the 1/4. So this becomes the 4th root of x, which again has a domain of, right, we've got an even power again, so x has to be greater than or equal to 0. Finally, we wanted to do g composed with g of x, which is going to be g of x. So in g of x, x minus 3, I'm going to replace it with g of x minus 3, which is x minus 3 minus 3, right? Use those brackets because g of x is one thing, right? So it's going to enter as one thing. And so we get x minus 3 minus 3. Oops, that's a nasty 3. There. Which puts me at x minus 6, which has a domain of, I'm allowed to pick any value of x and plug it in here. And so the domain here is x can be any real number. I'll just say r, or what I should be saying is x is in the set of real numbers. That's more proper. Okay. Using, oh, I haven't been keeping an eye on the chat, but there's nothing going on. Okay, so, but if you do have a question and you don't want to turn your volume on, that's fine. You can just ask it in the chat. But hopefully so far so good, maybe. Let's just do one quick example. Find f of g of 4 and g of f of 4, right? We can evaluate these new functions at values of x. If f of x, right, is, we're going to use these functions again, root x and g of x is x minus 3. So first thing we want to do, right, f of g of 4, well, f of g of x is x minus, or the root of x minus 3. So x has to be greater than or equal to 3. X equals 4, so that's allowed, right? And so here, let's just do it again for just some quick, oops. The root of g of x. Oh, and then I wanted the root of x minus 3, and the domain was x greater than or equal to 3. This is from above. So f of g of 4 is the root of 4 minus 3. The root of 4 minus 3, well, 4 minus 3 is 1. The square root of 1 is 1. Okay. X equals 4 is allowed since x is greater than or equal to 3, right? You always want to check that what you're plugging in is actually in the domain. If we move to g of f of 4, right? So g of f of x is f of x minus 3, which is the root of x minus 3. If we go back up there, g of f of x, well, the root of x minus 3, the domain, I'm allowed to put in any value of x as long as it's greater than or equal to 0, right? So x equals 4 is greater than or equal to 0, so that's allowed. So again, this is from above. Okay. And g of f of 4 is the root of 4 minus 3, which is 2 minus 3, which is negative 1. I'm going to keep it on this page, so a little lazy. X equals 4 is allowed since x is greater than or equal to 0. Notice that these two things aren't the same. We don't expect them to be the same, right? So I'll just make a note here. Notice f of g of 4 does not equal g of f of 4, right? That's just a good thing to keep in mind, that these two functions, the compositions of functions, even this looks different, right? Root of x minus 3 looks way different than the root of x minus 3, even though when you say it, it sounds the same, but it's actually quite different. All right, I'm out of time. Are there any questions?
You don't have any, so
let me know. You can always message me if you have questions, but
really
good. And so no class on Wednesday, right? Here, I'll just kind of scroll back up here, just so we know. No class on Wednesday because it's Remembrance Day. And so I'll see you on Friday, and we'll keep working through these compositions.
sounds good. See you
All
then.
right. See ya.